Well, I made this video to try to describe what we refer to as a critical speed when we do circular motion problems. And I've given you three examples here to start with, and I'll analyze two of them and I'll leave the last one up to you. The first is maybe something you've had experience with if you've driven, especially in wet or icy conditions, and that is there's a certain speed that you can go and still maintain a circular turn. So if you're turning on a road or just turning from one road onto another road, then if you go too fast, you're not going to be able to maintain your circular motion. So we're going to look at how we calculate that. The second one is for a marble to maintain its circular motion on the track. If we go too slow, the marble will just kind of fall off the track and become a little projectile. So there we're looking for not how fast, but how slow. And then the third example there is how fast can that roller coaster car go and not lose contact up at the position at the top of the track that we call Y, because if that goes too fast, obviously it's going to become a projectile in a similar way. So I'll start with the car turning in a circle, and then we'll look at the marble. So I'm going to make a little diagram here of the car that's turning in the circle. So make just a rough sketch of a car. You don't have to be a really good artist to be able to do this. Just like to do this so I can tell. So there's the tires meeting the road. And put taillights on it. I want to show it from the perspective of being behind the car. So those are the red taillights we use. And I'll put a driver here on the left. Now I'm making this in the United States. If you're watching this in a different country, your driver may be on the right. So this could be a little confusing, but we're looking at the back of the driver's head here, something like that. So to relate the forces with the motion always involves Newton's laws. So I'm going to start with a diagram of the forces acting on the car. We of course always have a gravity force, Fg, and we have the road pushing up on the car, and those two aren't terribly interesting because they're just equal and opposite to each other. That's what's keeping the car from accelerating up and down. But something has to be accelerating the car sideways because you don't turn in a circle unless you are accelerating. So keep in mind we're looking at the back of the car. This car is turning leftward, so there has to be a force leftward keeping it in the circle. The only thing that can exert a force leftward is the friction, or you might call it traction, of the road. So I'll draw a leftward force here and label it friction. And more specifically, and maybe surprisingly to you, that is a static force of friction. There's no actual sliding of the tires on the road. We're actually trying to keep that from happening. So this is a static friction force. There is no force forwards or backwards. That's because I'm going to assume we're going at a nice constant speed. We cannot have any tangential acceleration, and therefore we don't have any tangential forces. That would be along the direction of motion. So then we go to Newton's laws. If these are all our forces, Newton's second law will relate the motion with the forces. It starts somewhat generically with F net equals ma. And when I deal with circles, I like to start with putting the little c next to my acceleration. That reminds me that this is the centripetal type of acceleration, not the getting faster or getting slower type. Now, what is my net force that's causing the acceleration? I like to customize my equation by looking at my diagram and saying, what forces do I have in the direction of the acceleration? That's only the friction force. So I'll put that in place of my net force. I also like to put in the expression for the acceleration, which is v squared over r. Remember, I'm looking for a velocity, so I had to find a way to get that involved in my relationship, and that's where that popped in. So now, what is the friction force? Well, the static friction force is almost always less than mu times the normal force. But because we're looking for the critical speed, that means the very highest speed you can go. That means we need the highest friction that we can have. This is the perfect time to use the expression mu times the normal force. And that's mv squared over r. So now I'm going to replace the normal force with what it's equivalent to in this situation. It's not always equal to gravity, but it is here. And so I can replace that with m times little g, the strength of the gravitational field here. And then it becomes a little bit of algebra, just simplifying things. For example, canceling out the m's, moving the r over to the left side, taking a square root, and we will get an expression for this critical speed, just solving for v, of the square root of mu s times g times r. And I really like having it in this symbolic form because you see much better than you would with numbers what actually causes this critical speed to be what it is. It has to do with the coefficient of friction. The higher it is, the more, I guess, traction or stickiness you have between your surfaces, the higher your speed can be. Also, little g, the strength of Earth's gravity here. If that could magically get greater, then the car will be pulled down more strongly onto the road, and that would create a higher friction force. And then the radius, and this is probably the one you have the most experience with. If you try to go in a very, very small radius, you see you cannot have a very high speed. But if you, let's say, design a highway with a very large radius for a circle, that allows cars to have higher speeds. And that's exactly how the civil engineers design those things. So this is how we find the critical speed for the car negotiating a circle on a flat road. The ramped or the banked road is a lot more interesting. I'm not going to do that here. So let's take a look at this marble that's rolling around on a track, and we're looking at the very top at the moment where it's most at risk for leaving the track. And I want to find this critical speed. How slow can it go without actually becoming a projectile and just falling down and off the track? So I'll show this thing moving counterclockwise. And this again involves drawing a force diagram showing what would the forces be at the very moment when it's about to lose contact with the track. Well, we of course have the gravity force down. And for most of the trip around, we also have a normal force pushing perpendicular to the track. But when I want to find this critical speed, I'm looking for where that normal force vanishes or goes to zero. So I'm not going to include it in my diagram. So if that's my only force, that makes the Newton law stuff a little simpler, because F net is then just the gravity force. So I can say Fg is equal to m times the centripetal acceleration. Now be careful, don't carry this too far. This is one of the few times where the gravity force is also your net force. So I'll replace Fg with mg. I'll replace my centripetal acceleration with v squared over r. And then I'll do my little algebra move. And I'll find the critical speed for this one to be just radical gr. I don't have the mu involved because there's no friction involved in this one. But notice the similarities between these two expressions. And I will tell you that although I'm not going to show you the roller coaster, how it has a critical speed at which it can round that peak, it has a similar expression to each of these as well. If you can't find that, and you don't have a teacher to go to like me, then you can certainly go on the internet and find lots of examples of that. But I think I'm going to stop it here because this has gone on probably long enough. Hopefully that helps you understand a little better what we mean by a critical speed when we do circular motion problems. Thanks for watching.